I would like to introduce the first speaker today. And this first speaker is a longtime friend and the chief scientist at NASA, Dr. Jim Green. He was previously the chief of the Planetary Science Division, and before that was a heliophysicist at Goddard Space Flight Center. So Jim, take it away.
All right, thank you very much. Indeed, what I'd like to do this morning is, and this afternoon and evening for those, is talk about a time early moon when the moon may have had a significant magnetosphere. Next slide, please. And to begin that, what we want to do is be able to start with the giant impact hypothesis for the origin of the moon. And this, of course, is our leading theory, where an object about the size of Mars, soon after the proto-Earth and that Mars-sized object were formed, impacted, and then reaccreted into two major objects. One, of course, is the Earth we have today, and outside the Roche limit is where indeed the moon forms. Next slide, please. Now, the Roche limit is only a few Earth radii away from where the moon forms, and so over time we know that as the moon moves away from the Earth, based on tidal dissipation that occurs, it has this varying distance. So at approximately 4 billion years ago, the moon is approximately 20 Earth radii away, and then of course today the moon is at 60 Earth radii away from the Earth today. So that evolution is extremely important in this early period. Next slide, please. Well, a significant amount of work has occurred analyzing the Apollo samples, and this is for remnant magnetic field measurements. What's been teased out of the samples over the last several years in particular is that the moon's magnetic field was significant, particularly early on in its history. Of course, with the samples, we can date them and we make these sensitive measurements, and you can split over time what has been an intrinsic field from other effects that occur during this a major impact history of the moon. And so, for instance, the most recent paper by Magani et al. Has put many observations together. This figure is adapted from that particular paper, showing the region in white where the magnetic field measurements that have been coming from these Apollo samples over time. The inference these authors have come up with is that, therefore, the moon must have had a global intrinsic dynamo field early on in its history for several 100 million years, and then rapidly dies over time. Next slide, please. Of course, one of the big discussion points at this time relative to the analysis of those samples is, well, what is sustaining that magnetic field? And there are a number of ideas and theories about that, but although that's not the part that I want to dwell on in this particular paper, I want to begin with the concept that the moon, therefore, had an active dynamo for, although a limited period of time, and created, indeed, its own magnetosphere. So what we have done is we've done some basic modeling of the early moon magnetosphere based on those Apollo observations, and created a magnetic topology of not only the moon, but also knowing the Earth's magnetosphere in its history, have put these together relative to their positions. Next slide, please. Now, the modeling that we've accomplished has been done with some basic assumptions. These assumptions are where the magnetic dipoles of the moon and the Earth were anti-aligned, and we've also done that with the dipoles aligned. And so here are the basic topology results. Indeed, when the moon is at this early phase of it's moving away from the Earth, so it's approximately 18 to 20 Earth radii away when we see the maximum magnetic field that the moon is generating. And of course, we use the basic dipole of planetary science as the main component of that field to model. We have no other reason to believe we can tease out any higher multiple moments. So this is a first order analysis, of course. And so what we see in panel A is when the moon is ahead of the Earth, so this would be the moon in position on the day side, solar wind coming in from the left, of course, sweeping and interacting with these magnetic fields. And for dipole anti-aligned, we see a significant reconnection. In fact, it is a permanent feature providing strong coupling between these planetary bodies. Now, what we also see is closed field lines that come from the planet and then go back to the planet. Those will begin at Earth to fill up with evaporated ionospheric material. That region is what we know today, the plasmasphere. And during this time period, the extent of the plasmasphere would be significant because indeed the connection of the moon in this example provides many more of these closed field lines. Now, in addition to that, at higher latitudes, the field lines then reconnect the field lines of the moon and the Earth over in the polar regions. And this, of course, provides a significant opportunity for the exchange of low-energy ionized plasma along these field lines, typically emanating from the Earth to the moon, but indeed, it could go the other way. When the moon is on the day side, then, we also see in panel A that it provides significant protection against the solar wind. And that's of significance because many of the early theories on the evolution of the Earth during these time periods, we want to be able to maintain its atmosphere. Now, in panel B, we see, once again, dipoles anti-aligned, but in this case, the moon is on the night side of the Earth. Once again, strong reconnection, strong coupling is going on, and the same processes that I discussed with panel A is certainly going on in panel B. Next slide, please. Now, we can also examine this with dipoles anti-aligned, and there's no reason to think that, as we know, the Earth's magnetic field flips, the sun's magnetic field flips. We're assuming planetary magnetic fields beyond the Earth also go through a process of flipping. And so configurations that are the end members, the dipole anti-aligned, here's the other end member, the dipole aligned. Once again, solar wind sweeping these magnetospheres coming from the left. And what we see now, once again, is the moon on the day side, this would be in panel A, presents a significant barrier or protective barrier against the solar wind for the Earth. And we see, indeed, many more closed field lines with a lot of evaporated plasma. The plasmasphere must be much larger during these time periods. In panel B, we also indeed see the significant enhancement in the Earth's magnetic field. Density of the field lines indicate also the intensity of the field. And so you see where these field lines bunch up, those are regions of intense magnetic field. But indeed, even in this night position, evaporated plasma from the Earth would indeed move from the Earth's polar cap into the lunar polar cap region, even under the conditions of dipole aligned. Next slide, please. Well, what else is happening during this time period is that the early lunar magnetosphere is also in the time period of the late heavy bombardment. And of course, that means then the magmatic filling of these huge impact regions that end up creating the Mare regions on the moon. Now, Needham and others have proposed that during this time period, there's a significant amount of outgassing that's going on that would produce a tenuous lunar atmosphere of perhaps 10 millibar or so. Now, what's interesting, of course, that when you combine the eras of the magnetic field along with the era of magnetic filling and tenuous lunar atmosphere, that means the lunar atmosphere must also be protected during this time period by the lunar magnetosphere. Also, that strong coupling of the Earth's magnetosphere, as we saw, those magnetic field lines also will bunch up and also support holding on for longer periods of time the lunar atmosphere. Now, since the lunar magnetosphere lasted for only a few 100 million years, the atmosphere of the moon must quickly dissipate. But there's no doubt that it would leave its mark in volatiles on the surface. Next slide, please. So what must be happening then is being deposited in these permanently shadowed regions is a combination of volatiles from cometary, asteroidal material, lunar atmosphere, Earth atmosphere, and the current lunar water cycle we know today. Now, this stratigraphy wouldn't be so nice because of the micrometeor impacts, but some notional idea needs to be looked at. Next slide, please. So, in conclusion, the early Earth-Moon magnetosphere topology has been modeled. We use the giant impact hypothesis using dipole magnetic fields aligned and anti-aligned. And due to the weak but significant lunar magnetosphere, when it's only about 20 Earth radii away from the Earth, they're very coupled and they work together to protect the early atmospheres of both the Earth and the Moon. During the times when the magnetospheres had opposite polarity, magnetic reconnection would create a pathway for the atmosphere of the early Earth to be implanted into the lunar soils. And so for the Artemis program, we want cores. Significant cores in these permanently shadowed regions will be critical for us to be able to untangle this early evolution of the Earth's volatile, testing our model assumptions. Thank you.
Thank you, Jim. Wow, those are some pretty provocative ideas, and I think I can speak for the community and say that we cannot wait to get those cores. So that's fascinating. So let me, I neglected to introduce my session co-chair, who is, she was able to step in because the other one could not do it, but Licia Yeo is the co-chair, and I believe that she has a question for you, Jim. So Licia, please.
Hi, everyone. That was a really interesting talk. Jim, can I call you that?
Please,
yeah.
That's what I prefer.
So you mentioned that you're looking for cores from the permanently shadowed region. Why is that preferable to cores from just anywhere?
So indeed, there's been a fair amount of research about analyzing the regolith and finding nitrogen, N plus and even N2, and the concept is that must have Earth origin. So that's not just in the permanently shadowed regions. Indeed, that's from samples we brought back in the mid-latitudes. So the concept is, how did that get implanted? Well, there's been quite a bit of discussion on how that would be, and in reality, if this mechanism is working, it would be trivial to be able to implant that, because indeed that these field lines provide a ready pathway for Earth atmosphere to be implanted on the Moon at all latitudes.
Interesting. Thank you. We'll take one more question here, and it's from Yvonne Pendleton in the chat. Great talk, Jim. Can you help me understand how Mars lost its B field about 4 billion years ago and the Moon kept its intact so long?
So in terms of the Moon has an advantage in the sense that even though it's very small, It also is close to the Earth, and these tidal forces are really pushing on the interior and heating the interior of the moon. During the impacts, if we think about the late heavy bombardment, huge impacts going on, and then magma subsequently coming in, changing the mass distribution, that produces tidal forces that have to jerk the moon around to eventually what we see today, where the mass concentrations indeed are on this size. That keeps the core active. You have to dissipate that energy somewhere. And so I think that's an element of how the moon has maintained its magnetic field for several 100 million years. Mars, on the other hand, obviously didn't have other bodies, other things that helped generate it. It had even, the huge impacts disrupting it. It cooled quickly, perhaps. But indeed, it lost its field perhaps about the same time, at about 4,000 or 4 billion years ago.
Great. Thank you so much, Jim.
My pleasure.
Jim, thank you. Thanks for an excellent talk. Great way to kick off our second day at the forum.